the atomic and molecular structure of materials. Solids have a crystalline structure which corresponds to a microscopic arrangement of atoms that is repeated periodically. By staking planes, a 3D structure of specific symmetry can be formed. These structural arrangements result in a specific packing geometry that dictates the physical and chemical properties of the material, such as magnetization, thermal conductivity, or malleability. Reflecting X-rays off of materials can reveal the inner details of their structure. This video will illustrate the general principles of X-ray diffraction on a material and how this phenomenon is used in the laboratory to determine the structure and chemical composition of materials. To begin, let's have a closer look at a crystal. It is formed of atomic lattices disposed in planes, periodically separated by a distance d/hkl of a few angstroms. HKL are Miller indices, a set of 3 integers that constitute a notation system for identifying directions and planes within crystals. The smallest repeating structure in a crystal is called the unit cell. Different angles, alpha, beta, gamma, and lengths, A, B, C, of a unit cell forming the lattice will give rise to different symmetries. There are 7 crystal systems: cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. The relationship between the unit cell parameters and the Miller indices can be calculated for each crystal class. Electromagnetic radiation of wavelength lambda can have similar dimensions with the distances between planes within the crystal's lattice. These correspond to wavelengths in the X-ray spectral range. When X-ray light waves irradiate a crystal at an incident angle theta, they propagate through the crystal and encounter lattice points from which they diffract. Bragg's law relates these parameters, where n is an integer that represents the harmonic order of the diffraction. For a given lambda, only specific angles theta give rise to diffraction. This is the unique signature of a crystalline structure. In an experiment, the sample is rotated, and the detector that collects the scattered X-rays records peaks in intensity when reaching these characteristic angles. One can then extract the lattice spacing, d/hkl, for each angle satisfying the Bragg's law. Using multiple diffracted peak positions, corresponding to several distinct d/hkl values, the parameters of the unit cell can be solved uniquely. 2 main factors contribute to the relative intensity of the peaks. First, there are the non-structural contributions, which include the ability of the material to absorb X-ray light and the geometry of the XRD experiment. These can be taken into account in the post-processing of the experimental data. Second, and most importantly, the structural contribution of a material is carried to the relative intensities of XRD. Each diffraction peak is in fact the sum of all the scattered amplitudes from multiple ray paths diffracted by all the unique atoms in a unit cell. If scattered lights are in phase, there is constructive interference, while if they are out of phase, there is destructive interference. These interferences directly affect the amplitude of the XRD peaks, representing the HKL planes of the crystal. We will now see how these principles apply in an actual X-ray diffraction experiment. Before starting, carefully inspect the XRD instrument and assess its status and safety. XRD users must be trained in basic radiation safety before having access to the instrument. Then proceed with sample preparation. In this experiment, we use a nickel powder sample in the form of a pressed pellet. It is important that the sample is not thin, and it should be at least 3 times thicker than the attenuation length of the X-rays. Note that the following procedure applies to a specific XRD instrument and its associated software, and there may be some variations when other instruments are used. Load the sample in the sample spinner stage and lock the sample into position, making sure the irradiated side of the sample is parallel to the sample stage. Use a mask to adjust the X-ray beam size of the instrument according to the sample diameter. At the smallest incident angle, the beam must have a footprint smaller than the sample width. Now it is time to choose the acquisition parameters. First, select the angle range for the XRD scan. Typically, the range goes from 15 to 90 degrees. Then, select the degree step size as well as the integration time at each angle scanned. Next, proceed to the data acquisition. After the scan, a graph of the intensity as a function of the angle 2 theta is obtained. From this initial scan, select specific peaks and determine peak positions. Repeat the acquisition and focus this time on a narrower scan range around specific peaks, using a smaller step size and angle to obtain higher resolution data. Once the data acquisition is finished, data can be analyzed to identify the structure of the material. Using the instrument software and database library, each peak of the spectrum is identified and associated to a specific symmetry of crystal arrangement. In this particular case of the nickel powder sample, the spectrum shows a first peak corresponding to a 1-1-1 symmetry. The second peak is associated to a 2-0-0 symmetry, and so on. Then the software determines that this specific combination of symmetries corresponds to a face-centered cubic structure, and it identifies that the sample is a nickel powder. X-ray diffraction is a standard method for determining the presence or absence of crystallographic order in materials. It is often used to obtain a variety of other structural information regarding internal stress and defects in a crystal, or multiple crystallographic phases in composite materials. XRD technique is also used in biology to determine the structure and spatial orientation of biological macromolecules such as proteins and nucleic acids. In particular, this is how the double helix structure of DNA has been discovered, leading to the Nobel Prize in Physiology or Medicine in 1962. The study of the geochemistry of minerals, either for mining purposes or even for planetary exploration, also makes use of XRD technique. Think of the rover Curiosity on Mars, that has amongst its 10 scientific instruments an XRD detector to analyze the composition of the Martian soil,